Okay, this is our Algebra 2 Semester 1 final review, solving polynomials, which includes problems 9, 10, 11, 12, 17, 18, and 30. As a reminder, when you are given the directions, find solutions, find the roots, find the zeros, find the x-intercepts, this includes, saying real or imaginary. Slash complex. Finding all the roots, or finding the rational roots. At the end of the day, all of these different commands basically mean try to solve the equation. Now we do have lots of different methods of solving for x, and some of these commands are asking for particular portions of the solution set and not all of them. So if I'm looking at rational roots, I really only care about rational solutions. If I'm looking at real roots, I only care about real solutions, so nothing with imaginary numbers. So pay attention to what kind of solutions they're looking for, but at the end of the day, you're solving for x. So the way to find the roots, we have factoring and solving, which is almost exclusively what you're going to be doing. Using technology or using the rational root theorem. So to factor and solve, you can factor quadratics. You can factor sum and difference of cubes. And you can factor, remember, always look to factor the GCF, then factor more out of what is left. Right? So I might have something like 4x squared minus 100, and I'm told to solve that. Well, the first thing I want to do is find the GCF, which is 4. I'm left with x squared minus 25 equals 0. Which x squared minus 25 is that difference of squares? So we just do x minus 5, x plus 5. Set each linear term equal to 0. So the 4 equals 0 really doesn't do anything. It's a dead end. X minus 5 equals 0. X plus 5 equals 0. So this one will be x equals 5 and x equals negative 5. Using technology, so there's a couple ways you can use technology. Let's say you were given x squared minus 6x equals, and I said use technology to solve for this. Well, there's two ways you can do it. Method A, you can enter these equations in x squared minus 6x, y1, y2, x, oh shoot, just kidding on that x, just a 27. And then after you've entered it, go to second, calculate, intersect. It's going to graph the two functions. And if they don't both show up, then you're going to want to go to Window and just increase your Y values, most likely, because our Y value, one of them was a 27, so I'll make our Y max a 30. And just double check that. There, now both the graphs show up, so I'm going to go back to second calculate, intersect. It says first curve, hit enter because that is the first curve we want. Second curve, yes, that is the second curve. That's the second equation. Guess, for the first go around it doesn't really matter. And then you can see it shows the intersection as x equals -3 and y equals 27 at this point where those two parts intersect. So x equals -3 is one of my solutions. Then I go back, I just hit second, calculate, intersect again. This time I'm trying to get the intersection over here, this intersection, because there's two solutions since the power is 2. So you just hit enter for first curve, enter for second curve, but then for guess, you're really going to want to move the cursor towards that other intersection, or it's just going to give you back the first result that it already gave you. So it doesn't need to be exact, but you hit enter, and then my second solution is x equals 9. So now I know my two solutions are x equals -3 and x equals 9. And I'm done because my power is 2, so I know I found all of my solutions, at least my real solutions. The second method that you could use is to set everything equal to 0. So x squared minus 6x minus 27 equals 0. And then you would graph that, you'd get a parabola again. And then this time you'd be looking for the x-intercepts. This is actually a lot more complicated than just trying to find where the two sides of the equation intersect. So we're going to keep going. Using the rational root theorem is the third way that you can solve these guys, and that's your p's over q's, where p is the list of all possible factors the constant, and Q is the list of all factors of the leading coefficient. And then keep in mind that the solutions are when you take the p's over q's and plug them into the polynomial and they equal 0. And we will show you an example of doing that. So we can look at a couple of our problems. This is number 9 from the review packet. It says find the zeros of y equals 3x cubed plus 6x squared minus 189x. So we see that find the zeros. We know we're trying to solve. We should always try to solve using factoring first. So I can see 3x cubed plus 6x squared minus 189x. You can see that even I did not pull out all of the GCF the first time around. That's what these scribbles are. I realized kind of after the fact, like 3 and 6, ooh, I bet 3 goes into 189. Oh, it does, and I pulled that 3 out and kind of changed it up. So you want to pull that GCF out first. So I'll rewrite this line a little bit more clearly. So you pull the 3x out of the polynomial, and you're left with x squared plus 2x minus 63. So these are the easy ones to factor when that leading coefficient is 1. You're still going to think a times c. What are factors of this that add up to that? Well, factors of negative 63 that add up to 2 are a positive 9 and a negative 7. And then to get my first term, I have an x and x. And then I just bring down my 3x from the beginning. I need all of my factors there. And remember, we set each linear factor equal to 0. So 3x gets equal to 0. X plus 9 gets equal to 0, set equal to 0. And x minus 7 gets set equal to 0. So we solve those 3 separate equations, and we get our 3 solutions of x equals 0, x equals negative 9, and x equals 7. And that's just from solving by isolating the x, by adding the 7 to the other side, subtracting the 9 over, dividing by the 3. So another problem from our review packet is one where you use the calculator. So this is number 10, and it says find the zeros of this using the calculator. So I just use method 1. So I can show you that on the calculator because I obviously have the solutions right here. They are negative 1.31 and 4.17. So I can show that to you. Okay. So for this one, we're going to clear this guy out. And this is just using the same method as before. So our 2 equations are going to be the 2 sides of the equation. So we have x to the 4th minus 4x cubed. Oops, stuck up there. Is one of the equations. My second equation is going to be 12. And then when I graph them, just making sure everything shows up. That's my first side. And then this is my y equals 12. So I can go ahead and do second calculate, intersect. First curve, enter. Second curve, enter. Guess, doesn't matter for this first go around. And there's my first solution of the negative 1.13, which is right here. So we really are only concerned with the x value that makes the y value equal 12. So then we're going to have to go through again, second calculate, intersect, first curve, second curve. For the guess, again, you're going to want to go towards the other intersection so it gives you a new value. And that's where the 4.16 comes from, or the 4.17 when you round it. And that's it. That's all there is to graphing using technology, or solving using technology. Number 12. This is a problem that gave a lot of people some issues because you were really thrown off by the terminology. So remember, complex roots are just your imaginary roots. They have an imaginary component to them. And when you're being asked to find roots, again, the first thing you should see is, can I solve by factoring? So 4 terms. We always want to do factor by grouping, which is what we did here. I added in these little parentheses. And you just factor the GCF out of each group. So x cubed plus 3x squared, they have the GCF of x squared. I pull an x squared out of each term, I have x plus 3 left. 4x plus 12, I pull a 4 out of each term, and then 4 times x will give me a 4x, and 4 times 3 will give me that 12 back. So now, I have the x plus 3 repeating, and that is the GCF of the entire polynomial. And my x squared plus 4 becomes my other factor. So I just take each of these linear factors, well, they're not linear factors, but each of these factors, set them equal to 0 and solve them. So I have x plus 3 equals 0, and I have x squared plus 4 equals 0. I could have solved this by getting x to its by itself. But this is not a complex root. This is a real root, which is to say it's a real number. When I solve the second portion, the x squared plus 4, I subtract the 4 over. I get x squared equals negative 4. Sort of the in-between step that I didn't explicitly write out is that I took the square root of each side. So if I'm taking the square root of x squared, I get the x left. I always need the plus or minus, but plus or minus negative square root of negative 4 is the same as plus or minus 2 for the square root of 4, and I because it's a negative value. So this is my complex roots. These are my complex roots. Keep in mind that this is 2i and negative 2i, because whenever you have a positive complex root, you have its conjugate, which is the negative root. So again, anytime you are told to find the roots, you are solving. So that should be your first inclination, and you should try solving by factoring. Now, I did skip number 11 because it was a little bit different. So let's look at that. We kind of want to ignore number 12 that we just did. So find all the rational roots. So the rational roots are unique in that we really want to use the p over q's. So p is the factors of the factors of the constant. This is the constant. So things that go into 9 are 1, 3, and 9. And remember, you always need positive and negative. And then q is the factors of the leading coefficient, which is 2. Things that go into 2 are 1 and 2. So we take those and we make a ratio of our p's over q's. So that is taking 1 over 1, which is where this 1 came from, 3 over 1, which is where the 3 came from, and 9 over 1, which is where the 9 came from. But then I need to do it all again with 2 as the denominator. 1 over 2 is where the 1/2 came from, 3 over 2 is where the 3/2 came from, and 9 over 2 is where the 9/2 came from. Then I take all of these rational roots and I plug them all into the function. So I'm plugging all of them in for x over and over and over again. And remember, the fastest way to do that is to put it in your graphing calculator. So let's look at what that looks like, just as a reminder. So we go to our y equal, we enter our equation, the 2x cubed minus x squared minus 6x plus 9 equals 0. We want to look at the table of values, so we go to second table. Remember, everything to do with graphing goes up here. All the commands are up here. So you can see that it starts at 1/2. So we're on these 1/2s. So that helps us because then we can look at the negative 4.5, which is our 9/2. You can see that's where I got the negative 166. The negative 1.5 is 9. And so if you look up over here on your screen, just off of the video of the calculator, you can see these values. So it's the 9 and the negative 0.5 is the 11.5. Positive 0.5 is a 6. 1.5 is a 4.5, and 4.5 is a 144. Now if I want to see something other than those values of 0.5, or if they had been like whole number values and I want to see the 1/2, I go to table set, and for this I would start, it doesn't really matter, I just change it to a whole number. Keep your change in table 1, because you can always change where you start your table. So I'm going to go back to the table, and now you can see we've got our value of 1, our value at 3, and our value at 9, and then we can just scroll over to the negative side of things. -1 is a 12, -3 is a -36, and -9 is a -1476. So that's where I got all those values. So none of them equal 0, which is why there are no rational roots. No rational roots is stated right here. It is because none of these values were 0. If one of them had been a 0, that would be the rational root. Okay, here we have number 17. Number 17, again, you see that roots question. So you know you're solving. It has 1, 2, 3, 4 terms in it. So every time you have 4 terms, you're going to want to try to factor by grouping. If factor by grouping doesn't work, then use the rational root theorem, but factor by grouping will work a lot of the time. So we put our groups around the first 2, the second 2, and we factor those smaller groups. So 2x cubed plus x squared. We're just going to factor out those x squared terms because they each have an x squared. Pull that out, so x squared times 2x gives me back the 2x to the third. X squared times 1 gives me that x squared. In the second set of factors, 14x and 7, 7 is the GCF, and so 7 times 2x gives me 14x, and 7 times 1 gives me that 7 back, so I know it's 2x plus 1. So now I have the 2x plus 1 that repeats, that's my GCF, I pull that out. I have the x squared and the plus 7 that are left. That's my second thing. So since it says all the roots, we want to make sure that we solve each of these. So the 2x plus 1 gets set equal to 0. The x squared plus 7 gets set equal to 0. So if you kind of need to see this, 2x plus 1 equals 0. So you subtract 1 from both sides. Divide both sides by the 2, and that's where the -1/2 comes from. Similarly for the x squared plus 7 equals 0, minus 7 from both sides. And then we take the square root to get rid of the perfect square there, because those will cancel out. You will be left with x squared. with x equals plus or minus the square root of -7, which 7 is not a perfect square, so it's going to stay under, but because it's got that negative, that's where the I comes from. And then you just leave the positive 7 underneath. So we have 1 root there, and we have 2 roots there, and as a reminder, our number of solutions will always equal the highest degree of the polynomial. So that's 3 roots, 2 here and 1 here. So we are set with our 1 real and our 2 complex roots.
Do I put it in the oven?
Okay, so this one, what are the zeros? Zeros means find the solutions here. So it's already factored for us. X minus 8 squared, quantity squared, 2x minus 3 quantity, the quantity 2x minus 3 times the quantity of x plus 1. So when it's already factored, all you have to do is split them up. So we really just did x minus 8 equals 0, 2x minus 3 equals 0, and x plus 1 equals 0. So that's where these 3 solutions came from. The only reason this has a multiplicity of 2 is because it has an exponent of 2. Otherwise, you could write that these have a multiplicity of 1, but it's not necessary. We really only state the multiplicity when it's greater than 1. Two kind of related one, find the real or imaginary solutions by factoring this I just wanted to show you again. This is the sum of cubes. So this is a factoring problem, and you're going to have to know this. When you have a binomial with a cube, with the plus or minus, remember that's the a cubed plus b cubed turns into a plus b times the quantity a squared minus ab plus b squared. Or if you have a cubed minus b cubed, it factors into a minus b times the quantity a squared plus ab plus b squared. And so you're going to need to know that. That is in your book under factoring polynomials and solving by factoring. So we figured out that x cubed plus 4 cubed factors in x plus 4. And remember, I always did the first term squared and last term squared, and then in the middle I just multiply those two bases together. So we said each of those factors equal to 0. The x plus 4 results in this x equals negative 4. And then this x squared minus 4x plus 16, as a reminder, you're going to need to know the quadratic formula for this, because sum and difference of cubes don't factor those quadratics again. So the quadratic formula is x equals opposite b plus or minus square root of b squared minus 4ac all over 2a. And annoyingly, you can memorize that with the pop goes the weasel. And it goes x equals opposite b plus or minus square root of b squared minus 4ac all over 2a. Annoying? Yes. Effective? Yes. And a, b, and c in this case, your a is a 1. Your b is the minus 4 here. And your c is the 16. And so we just plugged that into our quadratic formula and started simplifying using our order of operations. We got to 4 plus or minus the square root of negative 48 over 2. Instead of setting up my factor tree off to the side, I sort of just did my factor tree here. 48 is 3 times 16. So 16 is 4 times 4 for a square root. If I've got those repeating factors, I can pull them out. The 3 does not have a repeating factor. It's stuck underneath. It was a negative, so I need an I. And then this last final step, I had 4 plus or minus 4i square root of 3 over 2. You look at all 3 of those items that are circled. They're all divisible by 2. And so I divided them all by 2, resulting in the 2 plus or minus 2i square root of 3. Okay? And 31, kind of related, you don't need to do any solving, but the polynomial function has the given roots, which are 3i, negative 5, and square root of 2. What is the degree of the polynomial, and are there any additional roots? If we're asking if there's any additional roots, there are probably additional roots. So you want to think about your complex conjugate, all these pluses and minuses, right? Anytime you take a square root, you have a plus or minus. So i's come from square roots. Square roots actually obviously come from square roots. So if you have an I or a square root, automatically its conjugate is a root. Now be careful, in this example both of my initial roots are positive, so we made the negative versions of them additional roots. And all together I have 1, 2, 3, 4, 5 solutions, so the degree is 5. But if you had been given the roots of 2, negative I, and square root of 3, then additional roots would be positive I and negative square root of 3. So whichever sign you're given for an I or a square root, you need its partner with the opposite sign, which is called a conjugate. Okay?